So now let's say we have a positive charge Q. We just got a circle. Consider that to be sort of an imaginary circle. And I've marked a point right here on the circle. I'd like you to make the same sketch and sketch the vector you think might represent the electric field at this point due to this positive charge at the center of the circle. So you should have paused and sketched that. And if you haven't, do so, because you should commit yourself. But the force is going to be, remember that the force exerted by this charge on any positive charge at this point is going to be along the line going through the two charges. If you have a positive charge at this point, it's going to be repelled. And you can go back through some of the details and see why, but that means that the electric field is going to be in the direction of that repulsion. So we could draw an electric field vector like so. Now, you might have drawn it longer, you might have drawn it shorter, but the idea is that if we were to put a charge here, if the charge is positive, then the field is going to be in this direction. Now, if you put a negative charge here, the field's going to be, not the field, but the force is going to be in this direction. The direction of the electric field, though, and if you go back to the way we defined it, you'll see why, is the direction in which a positive charge at a given point would be the direction in which the direction of a force that you would put on a positive charge that would result in a positive charge at that point. I don't know why I'm getting a little late, but I shouldn't get that mixed up, should I? Okay, well, hopefully you can work through my words and understand what I just said. It's the direction of the force that would be exerted on a positive charge at the given point by the field. Okay, now what I want you to do is go ahead and draw the field as it would be all the way around the circle. So you can pause at any time you want. I've just drawn 7 additional equally spaced points around the circle. So go ahead and sketch the field as you think it would be. Now let's assume that Q, your 0.004 Coulomb charge that we've used, at the -3 meter, 2 meter point, let's assume that this point represents that point and that we have this charge at that point and that the field is that of this charge. Then let's say that 10 meters, 7 meters, now your run is considerably more than your rise here. Your run from -3 to 10 is 13, your rise is only 5, so that you're here probably even a little bit below that, but let's assume this is your point. Sketch the field vector you think would apply at this point, if the field that we've sketched so far represents the field of this charge at this point. Well, I'm going to go ahead and do that. Hopefully you've done it. The charge would have to be along a radial line, so it would have to be out here. The force would be along a radial line, have to be out here, as the electric field would be along the radial line. And vector would have to be shorter than this because this point is further than any of these points. It would have to be longer than this because it's closer than any of those points. You don't want to get, well, it'd be a good idea if you could understand just how an inverse square force behaves and make a good estimate of how long the vector ought to be. Let's not worry too much about that. I'll just make a vector here that's fairly long but clearly shorter than either of these, and that vector would represent your 175 kilonewton I times I plus 67,500 kilonewton times J. Now I've sketched another charge, and excuse me, I'm going to call this positive charge Q1 now. So Q1 is your 0.004 Coulomb charge from before. I'm going to call this charge Q2. I don't really have a better notation. I don't want to use A and B. I wouldn't want to use 1 and 3. Now, originally we had a charge Q2 at this point, but we no longer have that charge Q2. We've divided it out to get the electric field so that our consideration of that charge Q2 is kind of in the past. So, yeah, Q2 was originally here, but it's not anymore. So I'm going to call this Q2. Now, I've sketched a circle. It's kind of not a great circle, but it's not a well-drawn circle. But I've got a charge Q2 at the middle, and I've got the vectors that represent the forces that would be experienced by charge. Actually, I've got vectors that represent the electric field at points around this circle, just as I've sketched electric field vectors for the first charge. And what I would like you to do is make your best estimate of what the charge would be, or what the arrow would look like at this point from this charge. Okay, so draw the electric field at this point that would be due to this charge, given that the vectors I've got here on this circle represent the electric field around that circle. Okay, hopefully you've done that. If not, pause and do it before I go into this. First of all, the vector will have to be radial with this, meaning along a line between Q2 and the point. That's going to put it at not quite a right angle, but something fairly close to a right angle to the electric field that we have from Q1. And the vector is going to have to be shorter than this vector. Now, we haven't doubled the distance, but we've made a fair change in the distance. So I'm going to say maybe this vector should look about like this. You might have drawn yours somewhat differently. As long as you drew it radial and as long as it was reasonably shorter than this one, I would say that you had a perfectly good drawing. So what we have now is we have at the point 10 meters, 7 meters, we have an electric field representing what would happen to electrical forces, what would happen to a positive charge at this point due to this charge and due to this charge. So that we have at this point, okay, this field and this field. Sketch, if you would, the net electric field that you would expect at the point. Okay, hopefully you've done that. Here's the field due to Q1. Here's the field due to Q2. The resultant field we can just sketch either by drawing the vectors head to tail or by drawing a parallelogram, but here's the resultant field. Now, if we had calculated the field, we would have gotten, well, we know what this field is, the 175,000 newtons times I plus 67,500 newtons per coulomb in the first one too, that times J. If I gave you the charge Q2 and its position, you could calculate it, and then you could simply add the components, find the magnitude and angle of the resultant vector. Be very simple. Maybe a little tedious, maybe a little messy, but ultimately simple. Just simple vector calculation. Okay, here's my sketch. Now the sketch should have two characteristics. One is all these points being at the same distance from the charge here, all these vectors should have the same magnitude because the force per unit charge is going to be the same, is going to have the same magnitude at every point that's at the same distance. Okay. Also, the field is going to be radial. That is, from the field at any point is going to be parallel to a line from the center to that point. And I'm not sure I really made it radial. This vector should probably have been turned a little bit this way. I wasn't all that careful. So you can see how well I did, and hopefully you did better. Not difficult to do. Most of them look pretty good. That one's kind of bad. Okay. Now, next thing I want you to do is sketch a circle at twice the distance and draw the field that you think would result. Okay, I've sketched a rough circle at about twice the distance, and I've marked points that would correspond to the points that I have on the inner circle. Okay, points at the same along the same radial line, a point along the same radial line as each of the points from the previous circle. There's no need to actually make those points along the same radial line, but I've chosen to do so, and you might think about what it's going to look like when we sketch in the resulting vectors. Okay, I've sketched the vectors, and they should be 1/4 the length of these vectors. So you cut that in half, you get a vector about this long. That's about what we have. I think maybe I made a couple of them short, maybe a couple of them are a little bit too long, but you get the idea. And this emphasizes the fact that the field falls off quite rapidly because we have an inverse square force. So that if the distance from the source charge doubles, we get 1/4 the amount of charge. And we could go on to a triple circle, and we'd have to make these vectors 1/9 as long as these. They'd be getting pretty short. We're going to need something a little finer than a piece of chalk to sketch those. But this gives you the general idea of the field of a point charge.